Hello, hello, good morning, afternoon. Oh, it was too soon. Yeah, that's my KiCad for Makers course link, but yeah, that is time for it. Welcome to the sixth part of this stream. Yeah, this design stream with STM32MP215F is definitely going to be never ending, but I made some progress offline after the recent session when I struggled with interconnection of the MPU and the DDR3L memory. Probably there is nobody from LinkedIn right now, but you can watch the stream like recorded stream. I posted about my founding on Monday on LinkedIn. There is a thing. Yeah, I can show you. I can show you because there is nothing easier. So here is my LinkedIn post, and yeah, this one. I found this application node by ST that I opened this guideline during the session, and actually it contains the mapping of the A0 to A7 ports on the MP215, which are, in the case of DDR3, hard-coded systemic signals for the DDR3 memories, and they are talking about some swizzling signals. Yeah, definitely you can change the position of the data and some address bits because there is some learning sequence and I don't know what else. And they mentioned a few mapping sequences or mapping structures or mapping schemes, and I didn't understand. Then I found a mention. I don't know if Gemini gave me a hint or in the guideline, maybe in the guideline. STM32MP215F tool has the DDR tool. I can open it for you, but if you choose the STM32MP2 range 215, for instance, then there is on the left pane, there is a list of peripherals. You can click on DDR, and in the center pane, in the center window, center part of the main window, there is this one, this DDR control PHY mode and configuration sub window. Then you choose DDR type, width and density, and it gives you an example mapping. But there is a validator, there is a check flag. You can see that this is okay. If you, for instance, remove one of the bits, you immediately see that the check is KO. Okay is changed to KO. So, or KO. So yeah. So I connected A2 to A7 according the guideline in the PDF, this AN5723, and then I connected the other signals from the example. I think I used the default mapping from the STM32MX from here. I don't know if this is the default mapping. Well, we can check. A8 is A0, but I have to check here. No, A8 is A0, yeah, then A7 A2, A9. Yes, yes, yes. This is the default mapping. I use the default mapping. I am not sure if it will work for my module, but there is a validator, and I believe in the validator. And I played a little with the validator, and the validator is probably not so smart. I don't say that it doesn't work. It does work, but it's not so smart. Like it checks, I don't know, some astral parameters of the DDR3 peripheral. It just verify there are all signals placed, all signals are mapped, and nothing is missing. So I kept the default mapping, and in the face of the PCB layout, I will tune the mapping for the easiest PCB layout. I don't know yet what will be the easiest layout, because sometimes even the crossed tracks can help, because you have to take the longer path, and then it can help with the length tuning. But we will see. We can always inspire with the default, with the reference designs, but all reference designs for 32MP2 contains DDR4. As I mentioned in the post, Andrea Cantone sent me a schematic snippet from his design with DDR3L modules. He used 2 modules, but on the STM32MP151, which is slightly different MPU because it supports up to DDR3, and the STM32MP2 family supports up to DDR4, and DDR3 is not the default memory device. So I have to dig into that. It means, yeah, shortly, the STM-MP151 has directly the CASN, RASN, and other systemic signals by default. There are dedicated ports for it on the MPU. But our MPU, as you can see, have only A0 to A31 and the systemic ports as I already assigned. So that was a long speech about the DDR3, but we can continue with now we can continue with other things. We have to assign the DDR power lines and some terminators, maybe, definitely grounds, definitely decoupling capacitors, and yeah, everything. So let's start with the power symbols, power nets. So VREF DQ and VREF CA. So let's check if there is ODT CA. I will have to open the data sheet of the memory. DDR1, VDD1, VDD2. Okay. I have to check the data sheet. Okay, let's do it. Here is our data sheet, and we are looking for the VREF inputs. Here is the table with all signals. VREF. Here, supply. VREF CA is supply. It's reference voltage for control, command, and address. VREF CA must be maintained at all times, including self-refresh, for proper device operation. Okay. Reference voltage for data must be maintained all times, excluding self-refresh, for proper device operation. Okay, so now I'm lost again. Never mind. MPU DDR VREF is here. not used for DDR4 in the reference design. That can be something. And I'm sorry for my missing knowledge, but yeah, I'm learning on the go. Okay, so let's open the datasheet for this. We have it here. And we are looking for the DDR VREF output, probably output is here. And DDR VREF, yes. Yeah, no description, only one occurrence. That definitely helps. So I am going to check the AN5723, AN5723, STCOM. I can close this because it consumes a lot of memory. I don't know why. Okay, so we are looking for VREF. VREF ZQ reset N. VREF observation only. Typical modes. General consideration about DDR3L. Device site VREF is generated internally, that makes sense. This is supply, it means it's input. Yes, input, supply. Yes. Reference voltage for control commands and address, reference voltage for data. So it means it's the power supply. Just the separate line to be noise free, most likely. Okay. The original reference design used DDR1 and DDR2. So let's check what they used. In power. Oh, but in the reference design, here, it's in the power block. Here, DDR1 is 1.8, and DDR2 is where? No, VDD2 DDR. Oh, here. It's 1.1. Okay. That's power supply levels for DDR3, DDR4. Okay, we have to check this data sheet. If we can change the yeah, probably yes, probably there is a reference voltage input. Oh, yeah, I can I could open the datasheet from the KiCad, but never mind. Okay. Now we are interested in VLX2. Default output voltage of the buck2 is nothing. So it means that the PMIC is configured then. That's good. BDD1, DDR, LDO3 is 1.8. It's configured or default? LDO3. Nothing. So it's configured again. Okay, that's fine because both outputs for the DDR is offline during the startup. Yeah, that's probably clever. Buck1 is in this case quite low voltage. Yes, the same. And the buck3 is again under 1 volt. Yes, 0.8. That's the, yeah, that's good. The LDO1, yeah, the rest is default. Yes, LDO6, yes, default. Okay, so DDR3 outputs are configured after the power up, and the core voltage, obviously, for CPU and CPU voltage is taken as default because, yeah, it can't be configured after power up because the CPU would be in danger or underpowered, or I don't know what. Okay, so we have two output voltages that must be connected to the VDDR, to the DDR memory, and are configured after power up. That's good. That's good. And now we have to decide what with the VREF voltages. Let me check this. Yeah, I'm checking the VRFDDR. Yeah, VRFDDR, and here is 0. Okay. And okay, VRFDDR. VRFDDR. Yeah. So, what are the recommended voltages for this? VDD of the DDR is 135, and VDDQ is again 135. I will connect these on the separate outputs of the PMIC because I don't know how to manage the excluding self-refresh and including self-refresh. And what does it mean maintained? Does it mean that it's connected or maintained like regulated? Don't know. Yeah. DDR-VREF on the CPU. We can open the We can open the reference manual for the MPU, pinout, datasheet. Okay. Yeah, that's again a slow stream. Yeah, but I would like to be more efficient and productive. But yeah, that's, you can see on the STCOM, it's a miracle of UX. When you open the main site, the search field is here. Yeah, so watch me, MP215F. And when you open the product page, yeah, it's still on the left side, but yeah, you will see in a while it will be on the right side. Documentation, reference manual here, and we are looking for VDDR_VREF. Okay. Once it's downloaded, now DDR_VREF. DDR_VREF is according this an output not used. I don't understand. Just 2 occurrences. Good. Okay. So we have more. We have guidelines for layout, and definitely in the layout there must be a note about here routing, and we want to look for VREF voltage, reference voltage, which is VDDR/2. Yeah, I understand the meaning of the reference voltage. It's like the middle voltage. Yeah, the DDR signals are going from 0 to the VDD voltage, and the level in the middle is the reference voltage, because it's too fast and they are going like in different pairs. So you have to know where is the 0, let's say. That's understandable. But how to generate the VDDR_VREF? I don't understand this sentence. The DDR3VREF pin on the STU is floating. It's floating. Okay, let's ask. STM32MP215F. There is a DDR_VREF port. Where to connect this signal, signal when using DDR3L module Connection strategy. Target voltage is half of the yes. Connection point. The signal must be connected both on the connection point. The signal must be connected to both VREF and VREF-CA. Okay, it means that there is an internal divider or a device that halves the VDD in halves. Okay. Decoupling cap, okay. Yes, that's our case. Dedicated PMIC. Exactly, this is that one we are using. Yes, typically paired with the MP2 series. If it often includes a dedicated VREF regulator specifically designed to track VDD-Q/2 and provide the necessary current. Connect the PMIC VREF output directly to the MPU and DDR3 memory pins. PMIC VREF, that's there's no VREF. That's I'm not smarter than I was before. But definitely we need this. Or not? Yes, it says that we have to connect DDR VREF and VREF DQ CA on the serial memory module. So I will connect the VREF through 0 ohm resistor and we can then tweak it later. So DDR VREF, yes, which is most likely output, but not sure, maybe bidirectional. I don't know. If the source is, no, the source is, I don't understand the PMIC node here. If it often includes VREF generator. No, there is no VREF generator. Or is? VREF. 0 occurrences. There is no VREF. There are only outputs. DDR2, VDD2 DDR, and VDD1 DDR. This must be 135, and this most likely 135 again. Because the memory datasheet says it. Okay. The VDD, no, the DDR VREF on the STM32MP215F is an output or input? Is an input. It does not generate the reference voltage internally. Instead, it requires an external stable voltage source to act as the threshold for DDR3 for DDR interface input receivers. Okay. Because it's an input, you must drive it with a voltage that precisely tracks. Okay. And okay. And on the DDR3L module, there are two VREF TQ and VREF CA ports. Are they inputs or outputs? Okay, so everything is input. So we have to add a source of the voltage there. Yes. Yes. Okay, so when using an external voltage divider, what is its typical composition? Only two resistors or 4 gaps. Five components, 2 precision resistors and 3 capacitors. Okay, so it's a divider in both DC and AC spectra. Okay, 1K to 10K, okay. The capacitor network filtering, this is where most beginners go wrong, because VREF is used for high-speed differential receivers. Any ripple on the VDDQ rail will show up on the divider. You need bulk capacitor, 1 2.2 micro to 10 micro capacitor, placed at the center tab of the divider, okay. This stabilizes the DC level. Decoupling capacitors, 2 100 nano, ceramic capacitors, one must be placed as close as possible to the MP215F. One must be closed. Okay. So yeah, naturally decoupling on IC side and bulk cap on the divider. Okay, and they say 0.1 tolerance resistors. Yeah, that can be done. Okay, yeah, that makes more sense, because our PMIC here, oh, we didn't do it yet, here doesn't have VREF output, and we theoretically can use the LDO7 out, but I don't think it's clever, because yeah, we won't do that. So we have new knowledge. This is input. More likely it's not more likely. More specifically, it's a power input where, what did I do? It works so bad. where a good decoupling cap must be used. Ground. Yeah. You maybe remember that we have to change all the grounds and power points and power symbols. So I can now place the final symbols and final power ports, power symbols. Okay, so this is the side of the MPU. Now we have to place it here. Not here. Here. What does it do? Here. And they say, yeah, that's, yeah. Let's ask Gemini, because it seems that this tool knows a thing or two. Please explain. Please explain the including self-refresh and excluding self-refresh part. In self-refresh, the MPU stops the external clock and stops sending commands to the RAM. The RAM takes responsibility of refreshing its, because this is dynamic memory. VREF-CA, including self-refresh. VREF-CA is the reference for commands and addresses. Okay. Why is what it says on? Okay. Excluding. Why it stays off during self-refresh? No data is being written to or read from the RAM. The data bus is completely idle and usually put into a high impedance state. Since no data comparison is happening, the RAM chip doesn't need, that's important. They doesn't say it mustn't, but it doesn't need. So it means that we can connect both VREFs together to our newly designed VREF voltage generator using 2 resistors and 1 capacitor. Yes, that's make more sense now. Optional in sleep, yeah, that makes sense, because you can save some power if you control the VREF TQ, but we don't need it. Perfect. That's finally starting to make sense. Do we need 2 caps or 1 only? H1 M8. Let's check the data sheet, the footprint. Where is H1 and M8? If are too far from each other, what did I do? No PCB editor. Footprint editor. Here. So they say H1, this one, and M8 here. We definitely need 2 capacitors. Because if it's so important for the communication and this must be stable, then we need to decouple both tracks, not just one. Okay. So we will do this. ZQ. They say we need 240 240 ohm resistor tied to VSS. So it means that we need 240. I don't know if we have it. We have, but I don't know if it's 1% or worse, or maybe better. This looks like 1%. Yeah. Do they require a more precise? I don't know. Let's ask Gemini, because this should be our clever companion. Let's talk ZQ on the DDR3L memory. The datasheet requires 240 ohm resistor to VSS. Does it need to be better than 1% resistor or not? %1 or better. Okay. Okay. 100 ppm they say. Let's check the Yageo parameters. Here it's 1% obviously and 100 ppm. I think it should be fine. Yeah, this should be fine. So this is 1%, and if I touch it, as you know, every time I touch component that doesn't have a GLC code, I have to edit. Yeah, I think I will use the same Yageo because the price is good. Yes. Yeah, there is a bug in KiCad because when you change the description, it doesn't appear here, but it's persistent from, I don't know, version 8 or 9. Okay, ZQ is our, I don't know what's this. I call it terminator, but it's probably not a terminator. Reference ball for output drive calibration. Whatever it means. Whatever it means, it's probably important. Yeah, based on my language, you already know that I'm a complete noob when speaking about DDR memories, but everything will be all right. Everything gonna be okay. No, that is much clever. You can connect here the line, then select it and drag it. See? This. Nice. Okay, so we have connected both DDR VREF lines, and now we have to create the actual VREF. Oh, probably somewhere here. So they say we need 1K 0.1% 0.1%. So surface mount in stock. I love 𝗂𝗂, not 𝗂𝗂 here. 0.1. We need 1K, so 1K, 1. This should be 0.0402, and here is our. It's 50 ppm. This is better for the same price. Okay, so we are using this because it's more stable. Here. So yeah, I will copy the 1K one because slightly less customization, 0.3%. I have to change the name because it would be in conflict with the other one. Datasheet definitely will be added. 0.1%. Here is the 𝗂𝗂. Yeah, I forget to copy everything. Datasheet, the GLC PCB. So we need 1K, 1. They say I think this. 1K only, okay, and we need 0.1%. That's good one. 𝗂𝗂, this is one. This is the one. Yeah, this is the same one. Oh, for a good price, yeah. So yeah, I have to make a short break. And here is the data sheet here. Fine, looks good. Looks good, and the value will be just 1K because it's in the description, and the longer values usually make some mess. Okay, before the break, as I mentioned, if you want to support me, I don't know if I can ask for it because my streams recently are not so great. But you can see here, KiCad for Makers is my course on 𝗶𝗶𝗀. You can design this board. It's for more advanced users. You can, but you can start with it, even though I described everything from 0 up. So yeah, that's one version. KiCad for beginners, essentials for KiCad. Everything is inside. There is a special offer if you enroll this course, either of them, you will receive a redemption, you will receive a coupon that you can redeem on the next PCB.com, and then you will receive not the bare PCB, but the PCB with all the components that you design. So you enroll the course, design the PCB, export manufacturing data, everything will be explained in the videos, and then you order the manufacturing at nextpcb.com and you will receive free PCB assembly. That's something, I think. Please, I'm back in a minute. This one. No, I will give this one the same voltage. Yes. Oh, it's already did. Oh, forget. Okay, so yeah, the attributes are not updated. Why? The selected symbol. So you have to choose that. Not selected symbols, it doesn't work. Update symbols matching rectifier, identifier, because then there are all attributes. Okay. Okay, then it work. Here. Output. Yes, and here should be one of the levels. Both will be the less noisy one. So as we saw, there are two. One is buck and one is LDO. I tend to use LDO, but we have to check the datasheet. Here, no. Here, noise. Let's say noise. Output noise. LDO out is typically 2.5. Yeah, but specifically, I will keep this LDO3. LDO 1, 2, 5, 7. LDO3 here. Noise figure is not here. Why? Why? So the LDO has 2.5 micro voltage RMS. When wall bucks enable 2.5 millivolts, so 10,000, 1,000 best worse. Never mind, worse. One noise. Okay, only one noise. Okay. So what? How they call the? They don't describe the noise. I will use the LDO, which is LED1. Will be LED1. Okay, so here, not here, and this will be input. In this case, I will use the labels and VDD1, DDR, okay, which will be output from the PMIC. This needs to be placed. Okay, so we have VDDR underscore VREF for the MPU and for the DDR. Nice. Then we have moved these ground symbols a little bit over here. Then we have VDDs. I don't know how many decoupling caps do we need. Let's try decoupling. Nothing. Capacitance. This is signal capacitance, but I'm interested in the decoupling. That should be in the guidelines for DDR routing. Yes. Decoupling. Each yes. I don't know if it fits there. How many caps do these? We have this original symbol here. Here is like million inputs, and they use like this number. Okay, not so much. The DQ was the resting one. Okay, so what they use? The VDD1. I'm losing track. The VDD1 was LDO, and the LDO VDD1 was connected to VDD1, but the VDD2, which is back, is to both VDD2 and VDQ. So it means that VDQ will be data, and what is the Q? CA was commands and addresses, and DQ was data, probably data. Commands and addresses, data pins, yeah, data. Okay, so it means, yeah, I was saying this, I use the same. So VDD2 is back and will be used for data. Here, yeah, here will be DDQ. VDD2, VDDQ, VDD2, and the opposite, what did I do? And the opposite will be CA or VDD1, fine. Here is like 9 and here 9. I don't know how many will be used. Yeah, I will use the same. So 4. More of them were on the VDD2, so it's our TQ, so more will be used here. I will use like 7 and 5. Let's say we will see during the PCB layout. At best, they would be 1 per input, but it's probably too much. Can we see the package? 0.0402, yes, and the bigger one 0603. Okay, makes sense. Okay, so 10 micro. X7R can be. Yes, all parameters are there. So 2 of them, and we say 7. Yeah, see, I will use all of them. So it means, let's say the 10 micro can be used as a decoupling for some pads as well, so 7. And if it's too crowded in the phase of component placement, I will remove some. Here. Six. I said 7. Here. And the number of is the same. Okay, so now it will be as before, but the same line, the entire line. Yeah, now it's perfect. And this is VDD1. Okay. It looks like we have connected the DDR3 module. And what's the time? 10:16. Okay. Okay, so this was connected. Yeah. MPU, yes. Yes. This is connected from before. PMIC. We mentioned this a million times, so let's do that. And it's, what's the name of this? Here, STPMIC, okay. STPMIC. This is the block. What was the? Yeah, and they use the eFuse as well in the same block. We can do the same. So as before, we can start with the imported project because it saves where are the data imported here, and it was PMIC, power PMIC, this one. Yes, Yes. Here's some mechanical part. Okay, so I will copy everything. Nice. And this is the original one. So ST1 S3 it is. Yes, ST1 S3. ST1 S3. Oh, probably I didn't create the eFuse yet. Oh, yeah, I didn't. Okay. So I need to do it. So let's start with the PMIC. 10 micros here. 0603. Okay, so as before. Input voltage at each one. This one has only 4 𝗶𝗶𝗀, probably. Some size constraints, but I'm not sure. I'll use all 10 micros and yeah, but we should find a clue in the datasheet of the PMIC if it's something here. Oh, it's input for internal audio and 1 and 4. Okay, and there are others. Okay, this one 1 micro, 4 micro 7, 1 micro. Yes. Why such a difference in it? Here. CV in. Okay, we can follow, and they are even the recommended part numbers. Okay. Probably not something that we should. Yeah, definitely we have a better one. This is X5R and we have X7S. Okay, but here. Okay, so CVN, it's readable. So let's start from the beginning. At the beginning is buck 1 in. 1 buck in has 10 micro to 10. Yeah. And there is PV in 5V in this, and it can be a global. Yeah, buck 2 in 10 micro and buck 3 in 10 micro. Okay. V in, which is 30, and 30 is V in for, yeah, these drawings are pretty good. Yeah. I'm considering drawing it as well, but not right now. CV in is 4 micro 7 to 6.3. So basically the same, but this cap is different. 4.7 micro or 4 micro 7, 6.3, 0.2. Yeah, this is the same. This is the same one. Okay, but I have to edit the library fields. Yeah, that's the one. Data sheet. But I say something about X7S. Was I wrong? It was the 4𝗲7. Okay. So here is the data sheet. Here is the part number, and here is the GLC. GLC code is here. Okay, KiCad. Here is the 4𝗲7. With this data sheet and this GLC PCB code. Yes. Okay, we have it. So LDO 25 in, it's not 25, it's LDO 25, but yeah. Where it is here? I think this, yes. LDO 25 in 1 micro to 25. Lots of components. At the best, I would use the same value as this one. I don't know. Okay. Yeah, and they probably mention part number. X5R. Oh, 5 million in stock. That's a popular cap. Micro to 25 volt. Okay, so, and for, yes, 0402. Okay, so I will create another one. Okay. So, data sheet, it's already there, and the GLC code is here. Data sheet is here. It's this X5R, new part number, and the GLC code is this one. Is it? Yes. Okay, let's do this. There is not enough space, so I have to go further from the symbol of the PMIC to keep more space for the LDO 3 in, which should be 10 micro to 6.3. I will definitely use the 10 volts. I don't want to have so many values in the schematic. It doesn't even make sense. And schematic is 6, 7, 1 micro to 25, the same as this one. Oh, 25. Okay, it's not 16 but 25. Have to correct it. So again, this one 25, yes. Oh, it's even 10. No. Yes. Yeah, the value. it's a mess. Yeah, you can see. KiCad doesn't sync the values in the property window or in this library window. There is still one 10 volts, but it's 25. You have to switch this to make the changes, and even the value must be changed, but yes. And we say the LDO67 yes, 1 micro to 25. By VIO is VDDIO, and VDDIO is what? VDDIO. I don't know. VDDIO is something. Here, 3.3. Oh, I didn't see it. Yes, here, sure. So VDDIO. Just the label. Int n is int n. No pull-up. PMIC int n. All the signals will be placed with the prefix PMIC. So SDA SCL. Okay. SCL is input. Input. SDA is bidirectional, but it's yeah, I will keep this one I2C S3. Yeah, we will see. We will see. I don't know if I will use the same I2C C3. Okay, I2C C3, and this is the same I2C 3, but SDA. Yes. Reset N and reset 0 ohm. Okay. Zero ohm, 0.4. Here, power control 1, 2, 3, all 0 ohms. See, I'm copying the on-grid elements, and yeah, now it works. So power control 1 is power on LP, power on LP, power on power on LP. No, this, yes, this control 2 is power CPU underscore on, CPU underscore on, and the third one is, yeah, I could even copy this. Yeah, I'm not the smartest one today. And reset flash CPU, and reset flash CPU, and reset flash CPU. Okay. Here are the grounds. GP 1, 2, 3, 4, 5. 2 and 4 are unconnected. XN is what? Yeah. XN1. I don't know. XN1. No occurrence. Okay. XN5, XN1. Here, it's a control for the. Okay, it's control for the. For this bug. Okay, which is that N5 is not connected. Just enable 1. And this is like, let 5 this. Disable display, I don't know. Disable, probably disable, because let yellow PMIC off. Okay. So label X1 enable. I can copy it. This will be definitely a label. The same here. Yeah, this can be, this will be changed after that. Okay, the LDO outputs. Yeah, I will copy this, the entire block. For micro 7, no, probably the data sheet, and that's int LDO output. Int LDO 4.76 per 6.3. This. Yeah, we have to save space. So this is this one without ground so far. LDO1 out. LDO1 out. Here are all outs. All LDO outs. 1, 2, not all. 1 and 2 has the same. Yeah, I can see it. I can see it here, but yeah. Okay. So this is this one. This is 2. This one. Now we have LDO4. The same. So it's chaotic. LDO2, yes, I need to draw these lines to see what I'm doing. Yes, LDO5. LDO5 is the same, 5, 6, 7. Okay, 5, 6, 7, the same ones. And that's good. 5, 6, 7, 3. What's the 3? LDO3 out is 10 micro. So 10 micro. LDO3 10 micro and 6 7s are 4 micro 7. I pressed the D instead of G. Not enough space. This and all the GPO. Okay, will be moved downward. Yes. Ground, 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 and ground. Okay, this can be deleted. The back outputs. I always forget that we have everything here. Yeah, here are some links, so we can delete it. I will use this. I will use the MIDI course. The power symbols, or it will be labels in our case. And they mention that all the outputs must be these and of a 0603 X5R. At least I think I have other ones or not? Probably not. 6.3. Yes. Yes, probably these ones. Yes, these ones. So just to add data sheet and the material. Material is already there. Okay. So these will be, yes, used, and The coil will be checked in a while. The inductor. Change symbols. These. Remove fields if not in the symbol. Yes. Yes, this is our symbol, but yeah, with the symbol replacement it will be a lot of work, but what's this? Internal. Oh, we don't need internal. We need external. Inductor 680 nanohenries. Package is 2016. Okay. Quite a. Okay. Okay. Uh, 2016. I don't know if I have. No. Oh yeah, here is one. Wait, 2016 is footprint. 2016 is 0806. That's not possible. Yes, it is. 016 is metric. Okay, so we have this. We have this part number. We have data sheet. What else? This IC code. Yes, that's the same. That's the same inductor. Okay. Yes. Yes. So we said this will be the value or name of the symbol. Datasheet 3.1, but 680 nano. It's non-shielded. It's the it's shielded. Okay, it's shielded. Okay. 43 milliohm, and they say what's the saturation current? 4.3. 1.3. Okay, here is the part number. This is the JLC code, and we are done. Okay, this is our lovely inductor. And this will be the label, globe label. Here and here. Nice. Nice. So what's the second line? DDD2, DDR, okay, the same, just 3 caps. And slightly these grounds are mixing with this is not the core. This is VDD2 DDR, VDD2 DDR, and 1.1. It's not the case. We have 1.35 volts. Yes. This one, and the third one is VDD CPU with 4 caps. Yeah, these grounds must be a little bit more safe space, space saving. And they say this is the description and VDD CPU. CPU with a long text on it, like this. Yes. And 4 caps, and this internal have only 4 caps. Okay, so this is our PMIC, and no, this is not. We are missing the labels here, which will be a slight issue because there is not enough space for it. Okay, internal LDO, not internal. Yes, internal has no output. This is the LDO1 label. Change to global. LDO4 can stay in this sheet. LDO4 is USB 3.3. So again, label, global, yeah, we are getting out of space. Okay, LDO. I'm always switching to another application because the IO is here already. Yes, LDO5 is VDD flash. LDO3 is DDR1, our famous DDR1. Yes. Okay, so more space, including this cap. LDO6 is this. W7 has no output. Okay, so this is the last label. Change to global. Yes, we can move these a little bit back. Yes, and the entire thing inside the sheet, DDR1 is there. Yes. Yes, we have PON key enable 40. Yes. Power on key, yeah, or PON key. Yeah. Yeah. I will use probably a different one. So it means tactile. I don't know. This one, maybe this one. This one is lovely. And 100 nanofarads. Oh, yes. Probably this one because the schematic will be full of them. And I am surprised that they don't use the SD diode. Which I definitely will. Three, 3.3 or bigger. PON key. Push button. VIO, which is 3.3. Okay. Yeah, it's not the greatest, not the best looking schematic element here, but yeah. Okay, the LED will be changed later, so I will make LED resistors. Yeah, at least. Okay, these are our test to-dos, and here is what is this? It's probably some loop. Yeah. So test point, I think I have called it Koralek, which is in Czech. The same thing. Yeah. Okay. We are 2 hours, almost 2 hours in the show, and yeah, good morning, afternoon, hello. Thank you for being here. I will continue next time. So thank you for being here. It was again a slow session, but yeah, I do my best and I can't be faster. I don't know why. Yeah, if you want to support me, KiCad for beginners at 𝗶𝗶𝗀, KiCad for makers on the same page, 𝗶𝗶𝗀.com. See you next week. Bye bye.